Hey, what's up, you guys? Yes, welcome back to another PY 212 review video. I'm Seven.
I'm Roger.
And I'm Mark.
And today we're going to be going over some of the questions on the good old practice exam. Let's go!
Let's look at one of our practice exam problems. So this one here, problem 4, is something you haven't seen before. So this is a Snell's law problem. And what that means is we're looking at different materials. We have two liquids, diamond and air, and we're looking at how light travels through these materials, and specifically at the boundaries or the interfaces of these materials where our refractive index changes. We can have two things that can happen. We can have reflection, which happens at the same angle to the vertical here, and we can have refraction, and that means essentially transmission. So we can have light come in to our interface and pass through, but generally in a different direction because of the difference in our refractive indices. And the way we determine the relationship between these angles is Snell's law, which I'm sure you've seen. And what Snell's law tells us is that our refractive index times the sine of the angle to the vertical here, the direction that's perpendicular to our interface, this product is conserved on either side of our interface. So n1 sine theta 1 is equal to n2 sine theta 2. And the way I've drawn this here actually implies that n2 is greater than n1. And the reason is we can think of n1 times sine of a bigger angle, theta 1, is equal to n2 times sine of a smaller angle, theta 2. So if theta 2 is smaller than theta 1, so are their sines, right? Sine of a smaller angle, at least from 0 to 90 degrees, is smaller. So if sine theta 2 is smaller than sine theta 1, then to compensate, n2 must be greater than n1. Okay, now, in this problem, like I said, there's 4 different materials: air, diamond, and 2 liquids. And what we're given is an initial condition. We know that in our first liquid here, our light initially travels upward with an angle of theta 1 equals 40 degrees to the vertical. And what we want to find is our 3 angles, theta 2, theta 3, and theta 4, which describe how this light is going to travel through our second liquid, our diamond, and the air. And so first, let's figure out some of the angles that are equal to each other here. So I've labeled theta 1, theta 2, theta 3, theta 4 just by definition, right? They're describing the angle with the vertical that our rays are making. But also, for example, if we start here, this theta 1 is going to be the same as this angle here. Got 2 parallel lines, and so these 2 angles have to be the same. The process of reflection physically is described by the angle, the incident angle being the same as the outgoing angle to the vertical. So all 3 of these angles are theta 1. And the same idea applies to the other domains here. So we've got theta 2 here, theta 2 there. I won't label these because there's not enough room, but I think you get the idea. Theta 3, theta 3. And it's helpful to do this because, for example, here, now we can see directly the same exact picture that we use for Snell's law, where the angles are labeled exactly the same. Okay, and from here, it's just going to be kind of reapplying Snell's law over and over to find these angles. So let's start by finding theta 2. So, theta 2, if we do some rearranging of our Snell's law, is the inverse sine of n1 over n2 times sine of theta 1. And actually, we know what our indices are. I've labeled them here. So for example, in this case, we have n1 1.3. So this is the same as the arc sine of 1.3 over 1.5 times sine of 40 degrees. Okay, and we can do this out, or we can leave it like this. For now, I'll leave it like this, and you'll see in a second why. Let's move on, and let's find out theta 3. So theta 3, very similar idea, except now we're looking at this interface here. We have our angle theta 2 coming in, and an angle theta 3 going out, and we know theta 3 is going to be smaller because n3 is larger than n2. Okay, and so we're going to have a very similar expression here, except now instead of going from 1 to 2, we're going from 2 to 3. So it's going to be n2 over n3 sine theta 2. And here is where we can either use the answer we get here by kind of calculating this out, or we can do something pretty clever, which is to say that we know what sine of theta 2 is from our Snell's law. And we can actually plug in our expression where we say we have our n2 over n3, and sine theta 2 from our initial Snell's law is the same as n1 over n2 sine theta 1. And you can see, if we combine these things, we get our n2 to cancel out. And we get an expression like this. And the physics here, there's actually an idea in this math, which is we don't need to know anything about our second liquid to know how the light is going to propagate here, which is pretty cool. So whenever we have two interfaces, we can ignore everything in between them to figure out our angles. So directly from knowing theta 1 and n1 and n3, we figure out theta 3. Okay. And finally, we'll get a similar idea with theta 4, where now we're going to go from our interface 3, our material 3, which is diamond, to air. So I'll write that out. And I'll use the same trick where instead of, taking our value of theta 3 and plugging it in, I'm just going to use the expression we derived. And you'll see why. So sine of theta 3, we can see, is just whatever is in this argument here. Because this whole expression is theta 3. And so we take away this arc sine, we get sine of theta 3. And same idea as for theta 3, we get that all our information about the third material, diamond, drops out. And so we get something like that. And so we can actually rewrite these, plug in the numbers a little bit. So N3 is 2.4 for diamond. And for air, N is 1, kind of the default. Okay, and at this point, we have our expressions for all of our angles. And physically, what these are describing are that our light comes in, part of it reflects at the same angle theta 1, part of it transmits with an angle theta 2 to the vertical. Then again, at this boundary here, part of the light reflects with an angle theta 2. Part of it keeps going with an angle theta 3. And finally, we have the same thing, except now that we're going from diamond to air, which is a larger to a smaller index, we get an angle in the air that is going to be larger than theta 3. And so that can be important because sometimes when you're going from a large to a small index, you can have something called total internal reflection. And what that means is that essentially this angle theta 3 could be too large to allow any light to transmit. Right? You can see as I increase theta 3, theta 4 is going to be larger. And so at some point before theta 3 hits 90 degrees, this theta 4 will essentially exceed 90 degrees, and we won't have any light going out into the air. And that total internal reflection you might have seen in lecture is the process that allows us to use optical fibers, for example, to keep that light inside the fiber. Okay, and finally, let's actually write out what our values here are in terms of degrees. So for theta 2, we should get 33.9 degrees. Yes. For theta 3, we get an even smaller angle, which is 20.4 degrees. And for our theta 4, we get a larger angle, because we're going from the diamond to air, which is 56.7 degrees. And so you can see we start off with 40 degrees. Our angle decreases twice because we're increasing our refractive index. Then we decrease it, and we get a larger angle. And that's problem 4 for you. Hopefully that was helpful. Yeah.
All right, so we're going to be working on problem 6 of the practice exam, right? So, the very first part of the problem, it's asking us to sketch what the intensity looks like for single slit diffraction, right? So the thing that we want to remember for this is basically just what this intensity interference will look like, right? So for a single slit diffraction, it's just going to look like this with one peak right in the middle, then it's going to die down. It's going to start off really wide, but then it's going to sort of die down like that, right? The thing that you want to remember about this is that the first maximum is going to be twice as wide as all of the other ones, right? You see how these are kind of the same width and this one is way bigger? Yeah, well, that's important, and that's something that you should know, right? It's asking for 7 maxima. All right, cool. 1, 2, 3, 4, 5, 6, 7. Great. 8 minima. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. On to some calculations. So it's asking us to find the wavelength of the light if we are given what the where the first minima is, right? So you might be wondering, which is something that I get confused too, is which one of these equations actually corresponds to minima for a single slit interference, right? And we can figure this out pretty quickly with a pretty simple derivation, right? So if we look at this picture right here, we can see that this is basically describing what is happening in our problem, just a little bit zoomed in, right? We can kind of picture this as the incoming wave is coming in like that, right? But there are two paths that two different rays of light could be going, right? So one coming from the top here, it's going to be traveling this distance right here, right? Pretty obvious. But the one coming from the center right here is actually going to travel a little bit longer than the first one is, right? In fact, the extra distance is just this distance right here. This distance is the extra distance. So, okay, if we know that the points at which these two match up, P1 is a point of totally destructive interference, then we know that the extra distance that ray 2 travels, it has to be off by a half of a wavelength, right? So this distance right here has to be 1/2 of a wavelength, right? Okay, cool, but we don't know what the wavelength is, right? So we want to relate that to the slit width right here, right? And so we know that this distance is a/2, right? Because we're starting the second ray from the middle of the slit, right? So we know that this length right here is a/2. Well, what's really cool is that this angle theta right here is actually also the same as this angle theta right here. So we can relate this extra distance traveled in terms of a/2, right? So this extra distance is going to be equal to a/2 sine theta, but it's also going to equal lambda over 2, right? From this, we can obviously see that these over 2's cancel each other out, and we get left with a sine theta is equal to lambda. And we see that lambda is actually being multiplied by an integer. In this case, our integer m is just equal to 1, right? There's no extra terms of over 2 or anything like that. So we know that for minima, we are going to want to use this equation right here. What we also know is that if this is for minimum, we know that this equation right here is actually going to get us the maximums, so the bright spots, basically. But since we're only looking at minima, we are going to be using this equation right here. We know that the length of the distance between the screen and the slit is 1 meter, whereas the distance here to the first minima is only equal to x is equal to 10 centimeters, right? Since we know that this x value is way smaller than this L value, we know that this angle here that goes from here to here, this angle is going to be really, really small. So that means we can use our small angle approximation, right? So basically what our small angle approximation says is that, well, sine theta is basically equal to tan of theta. And we know tan of theta is equal to x over L, or like opposite over adjacent, right? So we can use the small angle approximation to rewrite this equation right here in terms of x and L, right? So we basically have ax over L is equal to, since we know we're looking at the first minima, this m is going to equal 1, so we know that ax over L is going to equal lambda. So we basically have our formula for lambda right here. We know that a is equal to 10 to the minus 5. X is equal to 10 centimeters, which is equal to 0.1 all over 1 meter. So our wavelength of the laser that is being shown is 10 to the negative 6 meters. All right, so this next problem is a bit of a curveball, right? Because it's asking us what is the total number of maxima that we can see, right? So right off the bat, right, first let's consider what will determine the amount of maxima that we have, right? If we even look just at our first drawing right here, right, we know that there is going to be one extra minimum here compared to the number of maxima on this side of the screen, right? There's 1, 2, 3, 4 minima, but there's only 3 maxima, right? So what we can actually do is we can find the maximum number of minima that we can see, right? So this is our formula for minimums of the interference pattern, right? So in order to maximize our integer m here, we have to make sure that sine theta is at a maximum, right? Because a cannot change and lambda cannot change. So sine of theta has to be a maximum. Well, for sine of theta to be a maximum, sine of theta is just equal to 1, right? So in order to find the maximum number of minima, we have to set this equal to 1, so this just becomes 1. So m is equal to a over lambda, which turns out is equal to 10, right? So that means there are 10 minimums on both sides of the interference pattern, right? Like we said before, each side has one less maxima than there is minima, right? Each side has 9 maxima, right? Times 2 because there are 2 sides. But also, let's not forget the middle maxima right here. We also have to account for that. So that's going to be our plus 1, right? So this is going to just equal 19. So that means the total number of maxima that we can see on this screen is 19. All right, shifting gears a little bit, we are going to be talking about a double slit with a small slit size, right? So this is going to be a little bit different than what we've seen before, right? There's still going to be that one peak at x equals 0, but this time all of these maxima are going to be at a similar height and evenly spaced out, right? That's the thing that we want to consider, right? So instead of the middle one being super wide or anything like that, they're all the same width, and they all have really similar amplitudes as well. The diffraction pattern looks like this when the slit width is super small. Alright, so now it's asking us to find, since we know that the distance between minimums and maximums are the same, it's going to be asking us the distance between 2 consecutive minimas, right? How do we do that? Well, we know that for single slit, right, there's going to be a minimum when a sine theta is equal to m lambda, and a maximum for when a sine theta is equal to m plus 1 half lambda, right? But for double slit interference, it's actually going to be the other way around, right? So for double, there's going to be a minimum at d sine theta equals m plus 1 half lambda, and there's going to be a maximum at d sine theta m lambda, right? So if we're looking at the distance between minimas, well, we can use that same small angle approximation that we did before using this minima formula, right? Where sine theta is actually approximately equal to tan theta, which is equal to x over L. So what we can say is dx over L is equal to m plus 1 half lambda, right? So we can rewrite for x as this. Here we go. If we're looking for the distance between the two, we're going to be looking for x2. You can pick any 2 consecutive numbers, but I'm just going to do 2 and 1 because that's easier. x2 minus x1, which is equal to 5 halves minus 3 halves lambda L over D, which is just equal to lambda L over D. And if you plug your numbers in, you'll see that the distance between 2 consecutive minima are 0.2 meters. All right, for the last part of the problem, we are now looking at a double slit interference, but instead of A being small, this time A is not so small, and we actually have to take into its width into consideration. So when we're drawing this, right, basically what's going to end up happening is that the interference pattern from having a significant single slit width, there's going to be this envelope looking thing from the significant width of these widths right here, right? You're going to see something that looks like this, right? And so this happens as the basically the single slit interference from this significant width is acting as kind of a cookie cutter, almost, the way that I like to think about it, on top of this diffraction pattern that we see right here, right? So if you just kind of imagine we put this kind of shape on top of this, right? You can kind of see that this is the result of kind of combining the two using something called superposition. I'm sure that you've heard that phrase before. So this is effectively acting as the envelope, right? Whereas the red kind of line that I drew is what you're actually going to be seeing. It's just that as you go out, the intensity, there's going to be one bright intensity at the center, and then these ones are kind of a lot smaller. But yeah, that's problem 6 for you.